All right, so now let's shift toward indirect gas fired. So indirect, I mentioned the turn down capacity. Well, what exactly does 4-to-1 mean? Now remember, direct gas fired has 25-to-1 built in, but the math is kind of going to be the same here. So when we're talking about what 4-to-1 turn down actually is, you design a system around 6,173 CFM. You want to discharge 70 degrees on a worse design day where it's 10 degrees outside. Furnace capacity, 400 MBH required to get you that temp rise of 60 degrees. That's a typical design. Now the 4-to-1, your temp rise, you take your temp rise divided by that first number. So 60 divided by 4 gets you your minimum. Where this gets unique is we're getting into the season right now. We're finally, spring is here. So those outside air temperatures during the early hours and late hours, maybe they're a little cooler, but maybe you only need a 10 or a 15 degree temperature rise. Well, what does 4-to-1 mean when you actually have a 60-degree rise and what your minimum is? What if you have a 60-degree outdoor air condition and you still want to be able to discharge that 70 degrees? Well, with 4-to-1 turn down capacity, 60 degrees divided by 4 is 15 degrees. That's your minimum. So your minimum capacity now is still overshooting what your design discharge air temperature is. So that furnace is going to cycle on and off on those shoulder days. So high turn down capacity, very crucial. The higher the turn down, 25-to-1 built into direct gas fired equipment, now up to 16-to-1 with indirect gas fired, but obviously more costs associated with that. So typical is 4-to-1, and that's the math and kind of what that actually means. So the higher the available turn down, the tighter the temperature control that you'll have no matter what the outside air temperature is. So what does that look like? Furnaces fire on with an indirect gas fired heater. They fire in high fire, then they modulate down to its lowest firing rate. So here we're on in high fire, it modulates down. Our set point, we only need a 5-degree minimum temperature rise to achieve whatever our leaving air temperature is. Well, since it's 15 degrees is our minimum, it's firing at low fire. It can't do anything else but to shut down. So then it shuts down, and then it's bringing in whatever outside air has to offer. There's a cool off period required, and then we're below set point. So we fire back on in high fire, and then it's just a vicious cycle. So the killer of all equipment is obviously furnace cycling. Equipment cycling, anytime you can just energize a relay or energize a unit and maintain, always going to be an advantage. So 16-to-1, this is what that looks like. Furnace fires on in high fire. Your minimum temp rise now, if you do the math on that, 60 divided by 16, 3.75. If you only need a 5-degree rise, it can just sit there in low fire and just maintain all day long. And remember, 25-to-1 built into direct gas fired equipment. Now, the other thing to consider is, well, what about airflow? We allow 50% reduction in that same box in airflow. Now, what does that look like? We reduce our system down to same box. We're designing it for worst case scenario. You have that same 60-degree outdoor air day and you're at minimum airflow in that box right now. You just doubled your available temperature rise. So now that thing's going to cycle even more. So even your design temperature rise of 60 doubles to 120 degrees. And then at minimum, at 60 degrees entering air, your discharge air minimum is 90 degrees now. So that furnace is going to cycle on and off a lot more frequent if we're looking at lower airflow in that same box as well. So